This video is talking about an overview of Chapter 4. The content of this chapter is talking about applications of the derivative. Now, you must be wondered when we were talking about the derivative in previous chapters is that why do we really study the derivative? Well, one reason to answer this question is that it appears in many physical situation applications. Well, many physical applications have some mathematical equations related to them. These mathematical equations have different quantities. These different quantities depend on some variables or functions of some variable. Now, if we are interested to know what is the rate of change of this quantity with respect to this variable, then we are going to take the derivative for this quantity with respect to this variable. So one interpretation of the derivative here is going to be the rate of change. Another reason for studying the derivative is because the derivative gives you more insight about your function, which will help you to know your function more. For example, it will help you in graphing your function. How is that? Because if you evaluate what is the first derivative of your function, then you will be able to know what are the increasing and decreasing intervals that your function have in its domain. Also, you might be able to answer the question about the local and absolute extrema if your function have them. The second derivative of your function might help you to answer the question about the concavity of your function. So the increasing and the decreasing interval, local and absolute extrema, concavity, each one of these three topics has a separate section that's explained them in Chapter 4. By the end of these sections, you will be expecting to answer a fundamental question which is asking you to graph the function showing all the significant features. So keep a note of the following question, because after taking all these sections, you will expect to answer this question. The question says, graph the function f of x is equal to x times ln of x, showing all significant features. Remember, in the chapter when we were talking about the limits, we have some limitations with the tool that we used back then in Chapter 2. For example, sometimes you might face the situations some question asking you to evaluate the following limit. Limit when x approaches a for f of x divided by g of x. But you notice that this limit have the indeterminate form 0 over 0 or infinity over infinity. And with the limited tools that we have back then, we stopped. We didn't know if this limit actually exists or not. Actually, here in this chapter, we have a new section which is called L'Hopital rule. This rule actually is going to help you to determine if this limit exists or not in most cases. Now, what is the statement for this rule? Well, suppose that f and g functions are differentiable functions on an open interval containing the number a, except possibly at a itself, and that g prime of x is not equivalent to 0 for all x's in the interval, except possibly at the number a. If f of x divided by g of x is an indeterminate form, and the limit when x approaches the number a for f prime of x divided by g prime of x is equal to some number L, or plus or minus infinity, then that means the limit when x approaching a for f of x divided by g of x simply is equal to the limit when x approaches a for f prime of x divided by g prime of x. This rule is going to help you to be able to answer the question about the existence of limits for many situations that you were incapable of answering them in Chapter 2. Another topic which is related to applications, which is called optimization. There's a special section in this chapter which is talking about optimization. What does it simply mean? Well, in this section, it simply means that you are looking for the extrema of your functions, given that the variable of your function satisfying certain conditions. There are other topics that involve a derivative in them in this chapter. One of them is the mean value theorem. The statement of the theorem says that let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Then there exists a number c in the interval between a and b, such that f prime of c is equal to f of b minus f of a divided by b minus a. What does it simply mean, this theorem? Well, geometrically, it means that there is a tangent line at the point of tangency c and f of c, which is having the same slope as the secant line which is connecting the 2 points a, f of a, b, and f of b. Now you know from previous courses that if you have two lines with the same slopes, that means these two lines are parallel. So simply this theorem tells you that there is going to be a number at which the tangent line and this point of tangency for this number is going to be parallel to the secant line between the endpoints of this interval. Is this the only one? Is it just one number? No. Actually, sometimes you might have more than one number c in the interval between a and b, like what you've seen in figure P. So you have two tangent lines that's going to be parallel to the secant line. By the end of this section, you will be expected to answer the following question. Given the function f of x is equal to ln of x, prove that b divided by a less than e to the power b minus a divided by a for the numbers when a is greater than e and b is greater than a. Another topic in this chapter which is labeled with linearization and differential. Sometimes with some functions you are not able to find what is the value of your function at a certain point. Focus on the figure with me. Now at the point x, for example, the graph here, you don't know what is the value of f of x, the value of your function at the point x. So how you are going to use the tangent line or the derivative in order to be able to answer the question or to approximate the value of f of x? Well, we look for another point in the neighborhood of x, close to x, such that we know the value of the function at this point and the value of its derivative as well at this point. If we know the value of the function at this point a, then and the value of the derivative at a as well, then we are able to know the equation of your tangent line at the point of tangency a and f of a. Now from the figure you find that, or you could see easily, that is the tangent line here is close to the curve around the value of the point f of x. So, and in the y-axis you will find that the value of your function at the point x, f of x, is close to the value on the tangent line L of x, where L of x is going to be the value of your tangent line at the point x. Since on the y-axis the two values L of x and f of x are close to each other, then we could use L of x as an approximation to or approximation value for f of x. So we could have that f of x is approximately equal to L of x. How to find the value of L of x? Well, from the equation of your tangent line. F of a plus f prime of a times x minus a is equal to L of x. The last topic of this chapter is talking about Newton's method. Newton's method is a numerical method that will help you to find the solution of the equation f of x is equal to 0. Not all the time we are able to find the solution of such an equations analytically, so we might rely on a numerical methods to find the solution for such an equation f of x is equal to 0. One numerical method is Newton's method. Now Newton's method in its essence, it depends on the tangent line. How is that? Well, it's better being explained on the graph. So focus on the graph, the first one, part A. Now, from the graph itself, you know that the actual solution for this function f of x is equal to 0 is equal its x-intercept. So the value c. Now, if we can't, or if you don't know what is the value of c actually, then start with an initial guess, x naught. Now, at the point of tangency on the curve, x naught, f of x naught, draw a tangent line. Now, the intersection of this tangent line with the x-axis is going to give you another approximation for your solution, labeled x1. Again, do the same procedure again. Now, focus on part P of the graph. On the point of tangency, x1 and f of x1, draw another tangent line. The intersection of this tangent line with the x-axis is going to give you another approximation for the zero, which is labeled x2, and so on, like, until you get very close to the real zero, which is to the real solution of your function, which is c. Now, the success of Newton's method is dependent on the initial guess. If you choose your initial guess in a clever way and in a very accurate manner, that will help you to converge very quickly to the real solution. If you started with a bad initial guess, then that is not going to lead you anywhere, and you might just diverge from your solution, and it's not going to give you any answer for your question. Moreover, about this one is given in the section which is entitled Newton's method. As well, there is a specific video talking about this situation. That is all the key points that you expect to see in your chapter 4. I hope that you enjoyed this video and it's give you an insight about what you expect to get in chapter 4. So all the best and all the luck in studying this chapter.